Okay, let's now start understanding more what effective area is. So the previous video highlighted more on the concept of how uh, the critical path or the failure path is determined on the basis of staggered connections. No? So if the bolts are not staggered, then it's easier. That's why my first example gave you the staggered connections to highlight a few concepts on how the critical path or the failure path is determined. Okay, so let's move on to the evaluation now of your net area or effective area based on the net area AE. And to give you a more conceptual detail or understanding of this, let's try to enumerate first the factors influencing the performance of a tension member uh, in the manner it is connected. No? So the measure of its influence is called the joint efficiency actually, which has something to do on what you call the shear lug effect or the stress lug effect. And this efficiency is a function of five variables, which are the ductility, the spacing, the stress concentration, the fabrication, and the shear lug. And this is the most important, the shear lug that I explained to you initially on the previous video. So this occurs when all the elements of the cross section connected uh, are not connected on the connecting member. Let's say I have here an angle bar that is connected on a plate or a gasset plate here, wherein the two ends of the legs are actually the ones welded, not to the plate. So the stress concentration when you pull, okay, this angle bar will actually be more defined on the welded part only. Okay, so this is now your welded part, and therefore your stress concentration will actually be maximum at this point. If you look at the centroid of the angle bar, it is actually more on this vertex here. No? So the centroid of this bar is located here, which is very near this vertex. Okay, when you pull it on this location, then the shear lug or the shear concentration will be on the center. But on the other way around, if you pull this, okay, in a manner it is connected here on the end of the legs, then the stress concentration will actually be maximum at this end. Okay, so either way, the stress or strain distribution will no longer be distributed uniformly like this, and thereby causing an error on the computation of your stress in the basis of force divided by the area. So that's the biggest problem when you deal with this kind of connections. Okay, on the other hand, if we look in the next figure, wherein the connections are placed only on one leg, so particularly the other leg is not connected to the plate, then again the stress concentration will be maximum only at the portion where this member is connected to the plate, and thereby reducing the value of the stress away from this connection. So this interfacing point, or this interfacing location, is far of, from the end of this vertical leg here, such that you will notice that the stress is very small as compared to the stresses at this corner and at this part of the leg. Hence, shear lug is present in this particular connection. Now, when you talk of the computation of the factor U in terms of this understanding, then we have to follow some rules or guidelines coming from the AISC, based on two types of connection. The first one is the welded connection, and the second one is the bolted connection. So for the welded connections, we have two types of welds involved, no? So this is one, and sorry, this is number two. Okay, so the first type of welded connection is a transverse weld, and the other one is a longitudinal weld. Okay, so for the transverse weld, I'm not sure if I have your figure to. Okay, so the transverse weld is actually, let me use this figure above. Okay, for the transverse weld, we refer to the weld that is perpendicular to the tension force. Say this one is perpendicular to this weld here. Okay, meaning to say the direction of this force T here is 90 degrees to this direction of the weld. Then this weld is called a transverse weld. Okay, while this one, since it is parallel, the direction of this weld is parallel to the direction of the force, so you call this now a longitudinal weld. Of course, because of their orientation, the effect of such weld direction will also greatly affect the reduction coefficient U in this regard. So for the transverse weld, you just have to take note that the area of the connected part is actually the area of the effective part. Okay, so meaning to say, if I have here a transverse weld only at this point, then whatever is the area of this leg that is uh, uh, considered in your design will be exactly the area of the section that will be considered in the computation, or simply, okay, the area of effective on this cross section is simply equivalent to the area of one leg. Okay, so if this leg is not welded all throughout, then you just get the area where the legs are welded. Okay, so this is the area of the leg that is welded. So in this manner, you can now solve for the coefficient U in terms of course, this is a welded connection. There's no hole, the gross area. So simply my U here is simply uh, a, a, uh, a ratio of your area of leg welded divided by AG. Okay, so this is how you compute for the reduction coefficient for transverse weld. Now, for longitudinal welds, the AISC is much definite in giving us a value which is based on the uh, length versus width comparison. No, so this is L here is the length of your weld, while W is actually the uh, spacing between welds. Okay, so if I have here my figure on the longitudinal weld, your length and spacing W is given in terms of this. This is the length of the weld and this is the spacing of the weld. So the spacing of the weld is approximated to be equal, no? To be equal to the width of the member. Okay. So if this is a plate or an angle, so it's simply the width of the member. If this is a plate, it is the width of the plate. If it is an angle bar, it's the width of the leg of the angle bar. Okay, so this is now your W. And the length, of course, is measured on this basis, how long the weld was made. So question, can you do a longitudinal weld only on one side, then the other side is not welded? So those are the practical questions that might arise, and the code is not clear on that, but you have to use your engineering sense of judgment uh, to decide what to do. Okay. Okay. So notice that when the um, length becomes smaller, no, this becomes smaller than 2W but greater than 1.5, your U is reduced to 87%, and if it is smaller than 1.5W greater than W, it is 0.75. Now, what if your L is less than W? So what do? Okay, so you may reduce U further, but to what extent? Okay, so how do you reduce it? So since the AISC did not recommend, then it is safe to say that W must always be the length must always be at least greater than W or equal to W. So wag kang magwe-welding na mas maliit yung length dun sa spacing ng weld mo. Okay? So remember that. Now, other guidelines for welded and bolted can be seen on table D3.1 for the shear lug factors for connections. Okay, and these are the usual recommended values in case you cannot come up with a decision on what to do based on the formula or the guideline presented above. Okay, so all tension members where the tension is transmitted directly to each of the cross-sectional elements by fasteners or welds, except in case 4, 5, and 6. Ayan, may exception siya. your U is equal to 1. So which simply means that lahat ng members daw na naka-welding yung elements, 1 agad yung U mo, no? Kunwari, example of a section. Let's have a channel section. Okay, kung channel ganyan, and then naka-bolt dito, naka-bolt dito, naka-bolt diyan. Ibig sabihin, all the elements are bolted. Then U is equal to 1.0. Yun lang ibig sabihin nito. Kung naka-weld lahat yan, naka-weld dito, naka-weld dito, naka-weld dito, U is equal to 1. Why? Because the reason for that is because the transfer of the force, shear, will more or less be uniform. So the shear lug is negligible. So that's the meaning of it. Okay? So for, let's jump on number 3. For tension members where the tension load is transmitted only by transverse weld to some but not all the cross-sectional element, then the area of the effective area, rather, AE, is simply the area of the directly connected elements. So yun yung example ko kanina dun sa anong tawag doon? Leg natin. Ayan, yung leg ng angle bar. Ito. Okay, so the area effective is equal to the area of the leg that is welded. Okay, so yung number 3 pertains to that. For number 4, these are rather complicated situations wherein the welds are not the same in terms of the length because of the restriction of your connecting plate element. Okay, so you use this formula in terms of your L, okay? But the problem is, what are you going to use? L1 or L2? So I use the average of the two, okay? Others use the smaller, others use the bigger. So it's better to use the average of the two when it comes to this formula. So this pertains to all plates, angles, and channels with welds at heels, T's, and W shapes with connected elements where the tension load is transmitted only by longitudinal welds. Okay, for round HSS, hollow structural sections with a single concentric gusset plate embedded through the diameter, yan, nakalagay dito sa, nakapasok dito sa mismong pipe or circular section, hollow circular section. So you use this formula, X bar is equal to D over pi, and D is simply restricted to these values, and this D and X bar will now be used to determine your U on the basis of this restriction and this restriction. Okay, so you have to check where your restriction falls. Okay, so if I have here hindi kasi nakalagay yung ano, so just like a pipe, let's say this is your pipe and this is the plate. Okay, so this is the plate that is maybe welded, okay, on this side. So these are also longitudinal welds. So your L here is this one. Okay, so if this L is say 10 inches and your D is say 8 inches, so you just look into this criteria. Is 10 greater than 8 inches? is 10 greater than 1.3 of 8? If it is greater than 1.3 of 8, which I think it is, then, which I think is not, rather, then I use the other consideration. So, is 10 greater than 8 inches and less than 1.3D? Then if yes, I use this. So what is your X bar in this case? So it depends upon how your interfacing element is connected. If it is connected at the middle or somewhere above the middle of your circular section, then X bar is measured from there. Okay, so X bar is always measured from the centroid of the connecting member to the interface. Okay, so if this is now the centroid and this is connecting interface, then X bar is this measure. Okay, so these are normally given on the drawings that uh, you are provided in the design. So other cases defined on the table, 6, 7, 5, 6, 7, or sorry, tapos na tayo sa 5. 6, 7, 8 are also still for welded and bolted connection. So this is just the same with that of this circular, although there are differences in terms of computation of X bar here, because this is based on B&H, and then this is also based on B&H, but this refers to a plate connection wherein it is not inserted inside the center or the middle of the HSS, but rather on the top and the bottom flanges of the opposite flanges of the HSS. Okay, so if all the values here are given, then you can simply get your U on the basis of these dimensions. Okay, for 7 and 8, this refers more on bolted connections because we are talking here of fasteners in terms of bolts and rivets. Okay, so it has something to do with how many fasteners are connected. Okay, so we have here 4 or more fasteners, and here we have 3 fasteners. So you just look into the situation where it will fall and just get the value of U directly from the table. Okay, remember that this is applicable on WMS HP shapes, which I discussed on your steel sectional shapes, and these are for single and double angles. So 7 is for the standard WMS HP shapes, and this is for single and double angles, including T's. Okay, including T's. Nandito pa rin yung T's. Now, the question here is, what about the channel? Is it included here? Yung channel natin, walang nakalagay, di ba? So, does it mean na hindi natin pwedeng gamitin? Huh? What do you think? We cannot see any description on channel sections here. Yung tees, meron siya, ayun, or tees cut from these shapes. So where does the channel shape falls if you encounter a connection on the channel shape? Okay, so let's proceed with this one here. So the figure below shows the location of X for use in the shear lug formula. And this is the general formula in case you cannot interpret the situation on this table. And this is the number 2. So if you know number 2 formula, if you understand how number 2 works, then you might as well omit, no, the recommendation set forth on the other cases. Okay, so ito yung pinaka formula natin, no? And in this case, kasama na yung channel, no? Napansin nyo, no? It doesn't exempt any shape if you use this formula. The only difference is that for this formula, you have a limit of 0.9 as your value for this is the largest value you can get when you use this formula. So the problem now is where to find X bar or X, and this is simply the distance from the centroid of the element to the plane of load transfer, and L is the length of connection. So these are now the basis for this connection on the flange. Your L is this one, and your X bar is this distance from the top flange to the centroid of half the area. Okay, so you make use of your X bar now as the centroid here, the center of this T area. Okay, so where do you get the centroid of this T area? You just get the T section, then look at the table, or if not, you solve it using Varignon's theorem. Okay, so this is now X bar. So for channel, if you do a computation on the basis of these fasteners here, your X bar will be the centroid of the channel based on the vertical axis. Okay, so this is now your X bar. Okay, this is the centroid. Okay, so that's your X bar. If your channel has a bolt not on the web but on the flange, then you get half of the channel and then you get the centroid. Okay, what I mean, if it is not, the holes are not here, it is here, then you get the centroid of this on the basis of this as your X bar. So it depends where your connectors are, no? So it can change position immediately depending on the figure involved. Okay, for wide flange, ganun nga, no? So if this is the connection at the web, then your X bar is the centroid of 1/2 the part of this. Okay, so kunin mo yung centroid nitong kalahati niya. Okay, so ito yun. So you get X bar. If it is connected here on top, yung sa taas natin, yung sa taas ang gagamitin natin. And if you have a built-up section like this, or an angle bar, therefore your X bar will simply depend on the location of the centroid of 1/2 this part here to the transfer, or sorry, to the plane of load transfer, which is this connection. And so with this, X bar 1, or sorry, 2, and this is X bar 1. Okay, centroid to the element of the interfacing element wherein your connection is placed. Okay, and so on. So these are just figures for you to act as guide. There are a lot of situations that can be possible when you deal with the actual situations. But remember that understanding what shear lug effect is all about, and trying to be aware of the recommendations of, these are recommendations of the AISC, then the computation for you, for the value of u, will not be difficult. Okay, so that's it for the lecture on tension members. I hope you understood the concept in general. So I'll see you on the next lecture video. Thank you very much for listening.